Okay, thank you all for coming. And sorry about the delay. There was a trouble on everything. So let's start the first talk of this session. This is about contract satisfaction proofs and presented by Arthur Correnson.
Thank you so much. So I'm Arthur, and indeed I'm going to be talking about contract satisfaction proofs. This is joint work with Haoyi and Jana from MPI-SP. Okay, so the motivation behind this work is microarchitectural side channel attacks. And the context is that we have a program that we would like to execute on a CPU. And this program might manipulate all sorts of data, potentially some of which are secret. And the question we're asking is whether a potential attacker can recover secret data just by observing the CPU. And unfortunately, the answer is yes, via microarchitectural side channel attacks. And examples of such attack have been beautifully demonstrated over the past 10 years. And you might have been familiar, or you might have heard about the Meltdown and Spectre attacks, for example. OK, so the big question is, how do we defend against such microarchitectural side channel attacks? And one key idea is to verify that a specific program is secure to execute on a potentially vulnerable CPU. So the big idea is that we want to prove that executing a certain program on a certain CPU cannot leak private data. The problem is that, as I said before, those security vulnerabilities, they're coming from the microarchitecture. So if we want to prove this, it means that we need to reason about the way the CPU is executing the program at the microarchitectural level. And this is very tedious. So there is a solution, which is to use so-called leakage contracts. The big idea is to introduce a layer of abstraction in the middle, called a contract, which is going to approximate the leakage behavior, and we're going to prove security with respect to the contract rather than a direct proof with respect to the CPU. The big benefit of doing so is that hopefully the contract is describing leakage at a higher level of abstraction, typically at the ISA level, which makes verification much more tractable. But there is a catch. Of course, for this to work, it is crucial that the contract is faithfully approximating the actual leakage of the CPU. And this is sometimes called contract satisfaction. What we want to prove is that if we have a security proof with respect to the contract, we must be sure that executing the program on the actual CPU is also secure. And if we want to reuse the contract multiple times, ideally we would want to prove that for any program. And this is exactly the focus of this talk. How do we prove this contract satisfaction property? So existing approaches so far are either doing pen and paper proofs. Some people have tried to do testing directly against CPUs. Some people have tried Helmholtz model checking approach. And the question we're asking today is, can we also add like another level of guarantees by mechanizing those proofs in an interactive proof assistant, like for example in ROC or in Lean? And the short answer is yes, we tried, but the naive approach turns out to be quite tedious without formal foundations. So we're presenting two contributions. The first one is a principled, sound and complete proof technique for contract satisfaction proofs, and actually for a more broader class of problems. I'll come back to it in a minute. And this technique is called relative bisimulation. And the second contribution is to present a deductive system to simplify relative bisimulation proofs. Okay, so let's be a little bit more specific. What is the setting? So we suppose that we have a hardware semantics that describe how CPUs execute programs. We have a CPU state. The CPU state has a program. It might have some architectural information, like a PC, registers, and it might also have microarchitectural information, like caches, branch predictors, that sort of things. We consider that we have like a small step labeled operational semantics that describe how to transition from CPU steps to CPU steps, and that's labeled with attacker observations that model what an attacker can observe in between execution step of the CPU. And we're interested in collecting observations an attacker can make by observing the CPU starting from a given state. Okay, so with this setup in mind, what we are interested, or gold standard, is to prove non-interference. It means that if we take a pair of states that have the same public data but potentially different secrets, we want to make sure that we have the same observation. An attacker cannot distinguish those two states during the execution. So said otherwise, possible observation should be completely independent from secret data. So of course, proving this directly is very complicated because, as I said before, this property mentions the microarchitectural details of the CPU. And proof engineers don't want to look at that. So the idea is we introduce contracts, and what are contracts formally? They're basically just another label semantics. Just this time, the states do not mention the microarchitectural details, and we're going to try to predict the leakage instead of giving the actual observation an attacker can make, which we cannot because we don't have microarchitectural states here. Okay, so as for CPU semantics, we are interested in traces, like collecting the predicted leakage over time. Okay, so how do we use contracts to prove non-interference? The goal was to prove non-interference with respect to the CPU semantics, but we are not going to do that directly. Instead, we're going to split it in two parts. The first part is that we're going to use the contract as a drop-in replacement for the CPU semantics and prove non-interference there. This is nice because we don't have to talk about microarchitecture anymore. But of course, this only works if we have some sort of guarantee about the contract. And in particular, we're interested in proving that if we have equality of trace at the contract level, then we must have equality of trace at the hardware level. And it's relatively easy to see that if we compose, by transitive of implication, if we compose those two parts, then we obtain non-interference with respect to the CPU. Okay, so let's dissect a tiny little bit this contract satisfaction property. In a nutshell, what it says is we need to prove trace equality under a certain semantics, namely the CPU semantics. But we get to assume, to prove that, we get to assume that we have trace equality under a second semantics, namely the contract semantics. And ideally, we would like to do that for any program P. So how to do that? If we look a little bit more closely and we focus on the rightmost part of the implication, this essentially boils down to proving trace equality. And we do know how to prove trace equality. We just do a proof by bisimulation, right? It's that easy. Except it doesn't work because we don't have any assumption about the initial states. We cannot guarantee, like out of the blue, that those two traces will be equal. There is no reason to believe that they will be equal. So in practice, we actually really need to exploit the contract to prove trace equality. And this means that vanilla bisimulation will just not do the trick. So the key idea is to lift bisimulation, which is a binary notion, to a relative notion of bisimulation, which is a 4-ary notion. Okay, so before I explain how to do that in a little bit more details, I want to emphasize that the general problem we're looking at is relative trace equality. We have 4 traces, and we want to show that assuming equality between the first 2 traces, we can prove equality between the second 2 traces. And it turns out that it's a very recurring theme in PL and in security and maybe in other fields. So it shows up in secure compilation, in relative security proofs. And if you have other instances, please come talk to us. We are very interested. Okay, so one of the big problems when trying to prove this property is that we have 2 traces or 4 traces coming from 2 different semantics. There is no reason to believe that they're perfectly aligned or perfectly synchronized. And in particular, it might very well be that to prove an equality between the second 2 trace, we need to exploit an equality that happens at a much later point, for example, in the first 2 traces, and vice versa, by the way. Okay, so how do we do that? We introduce relative bisimulation. I'm not going to give you the full technical details because it's 11 in the morning and I don't want to bore you, but I want to emphasize a key feature, which is that internally, relative bisimulation is a nested co-inductive inductive definition, and the intuition behind it is that the outer greatest fixed point, so the co-inductive part, is here to establish equality between the 2 hardware traces, and the inner least fixed point is here to exploit equality between the contract trace. And the alternation allows us to do that in an asynchronous manner. Okay. A big theorem is that it turns out that this is a sound and complete fixed point characterization of relative trace equality, which is great because since it's a fixed point based definition, it means we can prove relative trace equality by co-induction induction. So this is all great in theory. I don't know about you, but personally, I really do not like to stare at fixed point equations. What I do like, though, is nice high-level proof rules and deductive systems. So let's do exactly that. Can we use relative bisimulations in a much more like user-friendly manner through a deductive system? So at its core, the deductive system we propose is operating on so-called proof quintuples. On the left, we have a pair of contract states. On the right, we have a pair of hardware states. And on the left of the turnstile, we have a relation R that's essentially a candidate relative bisimulation. You can think of it as a set of quadruples that we assume to already be relatively bisimilar. The catch is that this hypothesis is guarded, which I'm representing using like a solid box around the R. And at some point during the proof, it will become unguarded. And when this happens, we can exploit the assumption. This is actually reflected by the first rule of the deductive system, which is called the cycle rule. And that says that at any point in time, if the hypothesis is unguarded, we get to use it and finish the proof. So the whole game is to get to this point. How do we do that? We do that using the hardware step rule that enables us to unfold one hardware step from the current quadruple of states. And if we manage to prove equality of observation just for this one hardware step, then we get access to the hypothesis and the proof resumes with the successor states. Okay? So kind of symmetrically, we have the contract step rule that says that we can unfold one contract step. And this time we get to assume equality of leakage, and the proof resumes. The catch is that this time it keeps the hypothesis guarded. And the intuitive reason why, it's because this proof rule does not really prove anything, right? We are not making any progress. There is no side condition that we need to check. It's just generating new assumptions if we need them. Okay, so we've seen how to get access to the context, how to use the context, and how to generate new assumptions in an asynchronous manner. But the big question that is left is how do we store new things in this context? How do we extend our hypothesis for later use? And we do that using a co-induction rule that says that at any point in time, if we know that the quadruple of state we're looking at satisfies a relation R prime, we get to store this R prime in the hypothesis for later use. The catch is that the proof resumes, but from an arbitrary quadruple of states satisfying R prime, not the previous quadruple of states. You can think of this rule as a rule to establish incrementally a relational invariant. Okay, so that's actually about it for the deductive system. It's only 4 core proof rules that I find to be relatively simple and intuitive. It turns out that those 4 rules are giving us a sound and complete proof technique for relative trace equality. So in particular, we can prove that if a quintuple is derivable starting from an empty context, then this is equivalent to proving relative trace equality. Okay, unfortunately, in the interest of time, I cannot really give an example. It would require kind of a lot of setup, like giving 2 semantics and so on and so forth. But we did apply this deductive system to 2 challenging contract satisfaction proofs. The first one is a sequential contract that's essentially approximating out-of-order execution by sequentializing everything, and an always mispredict contract that is typically used to approximate branch prediction in modern speculating CPUs. I don't want to give too much more details, but I do want to mention that for both examples, the asynchronous handling of contract and software steps, hardware and contract steps, was absolutely crucial. Without this feature, the proof do not go through. Okay, so there are additional features beyond the 4 proof rules that I discussed. In particular, we can further equip the deductive system with so-called updo techniques to exploit symmetry and transitivity and simplify proofs dramatically. We also support weak traces, so a setting where some of the transitions might actually not be labeled with an event. And in that case, we can do pure asynchronous reasoning where every one of the 4 states progress independently from the 3 others. This is sometimes very useful. If you want to know more details about how the proof system works, or if you want to see example, the paper is already out. And if you're a fan of ROC proofs, please look at the ROC development. It is already relatively exhaustively documented. And with that, that's the end of the talk. And if you have any question, I'd be very happy to answer them.
Thank you. So it's now time for Q&A.
Case studies at the end, it sounds like you're dealing with models, not actual synthesizable hardware designs. And when I think back to the 2-step decomposition you put up there early on, 2 different, one equality and one quantified equality. What really struck me in the second property was that it quantifies universally over all microarchitectural state, implying that at any point in the kind of abstract execution, you have to be able to has to make sense to continue with arbitrary microarchitectural state, even though that state might in general be dependent on the architectural state. So that seemed kind of weird. And then also, in general, I think you'd be concerned about cases where on the 2 executions you're comparing, they have different microarchitectural state, but some reasonable equivalence relation
Yes.
connects those two together. So I'm just wondering, would you run into obstacles through the design choice you made that doesn't seem to directly handle either of those complexities?
Actually, this, you're absolutely right. This does not really matter in practice because you can very much add any assumption as you want, right? You can refine your assumption and start from states that are further constrained. Like relative dissimulation still applies, the deductive system still applies. So that would still work. And regarding your first remark, yes, we are working with models or very simplified models of CPUs. But the beautiful thing is that if you come up with a slightly more precise, slightly more realistic model, you can still compose the proofs, right? By transitivity, you can compose multiple relative dissimulation proofs and get the whole chain. So you can incrementally refine and go closer to like a more realistic model. So I hope this answered the two questions.
Yeah. Thank you.
Any other questions? We started late, so we can use time. I just want to ask one question. So is the use of R can be understood as a kind of instance of parameterized co-induction?
Yes. Yes, exactly. So internally, we are heavily using parameterized co-induction, and we're actually even using generalized parameterized co-induction because we need it for the up-to techniques. Yes, that's exactly.
I see. Any questions? Okay, if not, let's thank the speaker again.